So today we're going to be talking about kind of extending from Eli's lecture yesterday on different evaluation metrics. We're going to be going into a little bit of what Ethan mentioned, which is like beyond just a metric. How do you start to try to understand like what your model is good at and what it's bad at in a more nuanced way? And as a starting point, I just want to go back and re-emphasize a few things from the very end of Benny's lecture on how to train your model, because this stuff is important and is very relevant when you're thinking about evaluation. So the first thing is once you hit train, once you are training your model, you want to be able to track how that model is training over time. The easiest way to do this is you just print out, maybe loss results or accuracy results every epoch in your window. That is a totally reasonable way to do it. There's also tons of really nice tools, like the one actually that Ben brought up before, but one that a lot of us use really commonly is called TensorBoard. There's tons of different versions of this. Weights and Balance is another, but there are tools that help you track your model performance over time. And this can be like high-level evaluation metrics. You're picking just like maybe a single metric, or you can look at your loss versus your metrics and track them as your model trains throughout the epochs. And I just wanted to emphasize again the difference between a metric and a loss. The loss is the thing that your model is trying to minimize as it's training. A metric is some sort of evaluation criteria that you're evaluating. And those two things can be different, right? And you can have lots of metrics and you can even have lots of losses. You can track all of them. That's the difference in a loss is something your model is looking at to make decisions about how to optimize. And a metric is something that you're looking at to help you understand what's going on your validation set. It's pretty easy to use TensorBoard. I put some code that I copied from Benny's slides in here. But it's as simple as you just import this TensorBoard tool called a summary writer. You instantiate it, and then you literally just add this add scalar, and you name it something, and then you put the actual value. And so you're essentially just sending values to a specific name, and then it automatically will take that and generate all those plots per epoch of how those values are changing, which is really nice. The other cool thing, not that any of you have to do this, but TensorBoard is something that you can launch, and you can have it launch and actually display from your VM directly in a browser. It's just like an automated thing, so you push to a port. So sometimes if I'm training a really long model, I'll even just check on my model on my phone at the bar in the evening. Just be like, let's just make sure it's not doing anything crazy. You can actually just check your model performance really easily in a browser, which is nice.
Sarah?
Yeah.
Is Comet another synonym to this?
Yeah, so Comet is maybe even one more layer. So TensorBoard, you can pull up a TensorBoard and point it to multiple experiments and directly compare the plots for all of them. Comet is something that takes that to a slightly additional level, where it does a lot of the infrastructure for you to be able to just visualize and point to all your experiments at once in there. I would call them different flavors of the same type of thing, which is a tool you don't have to write that makes it easier for you to track what's going on with all your experiments. So another thing that is really important to point out as you're going through this process of training models is saving checkpoints. So basically this is saving off the entire state of the model at different points in time during training. So here what you're doing is every epoch, for example, you would actually save all of the parameter values, all of those weight values for the model, as well as potentially some other things you might want to save, stuff you can define what you want to save, but the training loss, the validation loss, maybe the set of hyperparameters that are being used. And it's really simple in PyTorch. You can just use torch.save, and you save it to some sort of file. The cool thing here is that then it means that you can point to any one of those checkpoint files, and you could start training from that point. You can also load in any of these checkpoint files and use them on new data to evaluate them. And sometimes training can be a little finicky, something might go wrong on the GPU, and so you might have something go weird at some point during your training where something crashes. this gives you the ability to just point your model to the checkpoint right before something went wrong and keep going instead of having to start from scratch every time. And then once you have a checkpoint saved, loading in those weights is as simple as just torch.load. And then you just put those parameters in the model that you've instantiated. So one of the things this is super useful for is actually that once you have this model, you have a checkpoint, now you can use that checkpoint and you can apply it to a bunch of new data. And a slight aside, before I get into some more of the evaluation stuff, we realized we hadn't taught you guys this, but it's kind of useful. We made a tutorial on it, but essentially you can use something like GNU Screen or TMUX. We're just going to teach everyone Screen for now because it's automatically included on your Mac and on the Linux machines. But essentially something where inside your VM, you have your terminal window. You can now open up like a different terminal window and you can sort of jump to it. Like it'd still be within the same window, but you kind of like pull up like a new window in a screen. And then you can run something and then you can like move away from that window. So now it's running in the background. And so if you're going to launch training, for example, this means now you have a process that you can, and then you can go back in and look at how it's doing and leave again. Now you have a process that's running entirely on your VM that's not reliant on your browser staying connected to Wi-Fi. So if you start training and it's going to take a couple hours, you can do this in a screen. You can leave the screen, you can close your laptop, and training will continue to happen. Whereas if you just have, this screen and you guys are working with laptops, if the Wi-Fi gets flickery or something, you can have weird stuff happen where the training will crash. So we have an example of how to do this, but it's pretty straightforward. It's basically just a way to make sure that the processes that you're running are on your VM are disentangled from the SSH connection from your local laptop. Cool. So what is my model doing? How do we dig into performance? So the first thing that you need to do in order to get something beyond just a single metric, what I like to do is write a prediction function. This is essentially a function that does not assume that you have ground truth. It's not necessarily going to have like this direct comparison to ground truth, but it's just going to generate results for a new set of images from using a given model checkpoint that you have. And so basically what you'll do is you'll have a data loader. This could be a data loader for your training data, for your validation data, for your test data, for completely new data that you haven't actually considered yet. And it will just generate predictions for all of that data using your model and then save those predictions to some file. You get to decide what you want to save, but the point is that you have now a function. You can point it at data that's coming in from the data loader you created and get results for every single image in that data set. So what else might you want to save besides just like the prediction? If the prediction is like, I don't know, an example from one of yours. With Carly's model, the prediction is lemur exists or lemur doesn't exist. So you could save the prediction for that window of lemur exists for every single example, but what are some of the other things we might want to also know besides just the model thinks there's a lemur or not? Any ideas? Yeah.
Maybe like the percent confidence?
Exactly. Keeping the confidence of the model is super useful because then we can start doing some of the things that Eli was talking about, like sweeping over different confidence values, looking at different stuff. Any other ideas?
Like any label encoders or scalars that you've applied?
Mm-hmm. Yeah, totally. So yeah, like keeping track of maybe like, I don't know, what you just said was kind of pre-processing. One thing that people often forget but is super useful to have in these files is just make sure you save again the paths to the original images. So that then if you want to look at the results on your images, you don't have to like go figure out how to find what the image path was again. It's just right there in the same file. And then the other thing is sometimes it's nice to keep the logits. So usually the final classification layer will be some sort of projection to a layer that has the same number of, in a classification problem anyway, the same number of outputs as your number of classes. And then we take a softmax over those values. But there are sometimes nice things that you can do pre-softmax. So sometimes I like to keep off the logits as opposed to just the final after the softmax. Yep.
What is a softmax?
Oh, a softmax is a softmax is a function that basically maps values in sort of any like space to values between 0 and 1. So it's mapping your sort of model output values to something that's interpretable as a confidence. But it's just a standard function that just maps to something between 0 and 1. Okay, so now once we have predictions, so once we've written this prediction file, run it on some set of data that we want to look at, now we can start poking our model. And I thought it would be fun to go through the process of back in 2017, early on in grad school, when I started trying to look at species classification and camera trap data, working with a few different groups around the LA area, and the ways that we tried to visualize results of our model to try to understand what was going on, and then some of the decisions we made after the fact based on those results. Just because it's a nice, very concrete example of like ways that this type of poking beyond just a number really gave us a lot of information. So super high level model details here. We were not doing detection yet. This was pre-mega detector. This is just full image classification. We were fine tuning our model from a model pre-trained on iNaturalist. So it did already have, like Ben was talking about earlier, it knew what red was. And we had 30 categories, and they weren't all at the same taxonomic levels. There was like bird and small mammal, but there was also like cow. What we had done for this split is we'd taken 10% of the data from training locations, and we'd randomly held that out, and that was our in-distribution validation. And then because we already knew that we wanted this to work for new cameras, we had taken out 4 locations for testing. We were working with 4 projects. So this was basically just 1 location per project that we held out at random. So just some high-level visualization, just like poking our data before we even start poking the model results on our data. This is a grid of randomly sampled images of bobcats across the data set. And here what you're looking at is the number of bobcat images per location in the data set. So you can see there's bobcats shown in a lot of different locations. There's a good amount of variability in what bobcats look like. All of these plots are going to be on log scale here on the y-axis. So just recognize that this is not linear scale. Stuff that's high is a lot bigger than stuff that's low. Mountain lions, this is a species that's significantly of interest in Southern California. You can see here that there are many less examples, both in terms of the sheer volume, but also in terms of the number of locations where we had examples of bobcats. And that's reflected in what these bobcats look like. You can see there's like sort of starting to get a lot of repetition in the examples of bobcats in our data. Also looking at cows, here we actually only had cows at 3 locations, but there was a good amount of them. And you really can start to see how repetitive the data starts to look when you have less variability. So looking at just single metric results of this classification model, top 1 accuracy on that randomly held out in distribution validation set was very high, 96%-ish. And then if we took an average over those held out test locations, it was close to 75%. Okay, so there is this drop off in performance. But even just here, we can start to break this down. So if you just look at now the per location performance, you can see there's a lot of variability. This C4 location, the accuracy is actually almost as good as the in distribution set. And then this, Mexico location was really hard, like around 60% accuracy. And note here, this is just vanilla accuracy. This is just how many did we get right. Okay, let's look at training results. Evaluation is not just for testing. And one of the really nice things you can do is you can run your prediction strip on your training data and start to try to understand what is hard and easy about your training data. So this is just looking at the number of annotations we had per class in training. You can see there's a lot of variability. If I was redoing this now, I would probably sort these in order of the number of samples to easier to interpret, but I did this in 2017. I've learned some things since then. So one of the things we started poking was looking at on our training data, precision and recall normalized confusion matrices. So a confusion matrix basically is something where you can take, especially if you have multiple classes in your training data set or in any data set, you can look at what's going on here is this is the left side is the true label of the model. And this is sort of like the values here are between 0 and 1. So here, these are like the ones that the actual label is small mammal and our model predicted small mammal. And then this is the proportion of those that are sort of in the right thing. When we say normalized by precision, so essentially we have this matrix, you can build it for the raw numbers and you can get like, okay, this box we got, out of the 200 small mammals there are, we predicted 198 were the correct thing, and you can just get a concrete value. But then you'll often, because of the imbalance in data, it's really hard to see sort of all at once. And what you'll get is something where you get these really dark boxes just on the most common things. So then you can choose to normalize that matrix, but you basically have to choose to normalize it row-wise or normalize it column-wise. And remember, Eli was talking about precision versus recall. Precision gives you a sense of the things that are actually, of the things that you predicted are a given thing, how many of them were correct. So if I predicted a lot of stuff is wolves, how many of those predictions are correct? That's your precision. And so if you're normalizing in a sort of precision sense, it's giving you a sense of, like you're basically normalizing, let me think about this. I'm probably gonna say this wrong. If you want, I think it's normalizing column-wise. That might be wrong. But anyway, you're either normalizing column-wise or row-wise to give yourself the sense of all of the things we're predicting to be this, how many are correct. Yeah, you're normalizing column-wise. So you're normalizing in the predicted dimension, basically. And here you can see that some of this stuff is pretty hard. Like, for example, things that we're predicting a lot of stuff to be rabbits that isn't rabbits. We're predicting.
What do you normalize it by?
Huh?
What are you normalizing it by? What value?
Like it's straightforward, just column-wise, you just sum the values in that column and then divide all the immediate things by that. And row-wise, this is now normalized by recall. Now we're saying of all the things that actually were wolves, how many of them did we find? And so this is a sense of like precision is like, are we kind of bad at what we think something is? And recall is more like, are we finding the stuff? Are we missing things? And you can see here that from a recall perspective, it's quite interesting. We're sort of better at recall than we are at precision in a way here on the training data. Here's another way to visualize that, like a similar thing. And now here we're looking at the number of training annotations that we have. So this is like the number of annotations. Here, this is just a per class dot. And here we're looking at the percentage of mistakes. So basically the error, 1 minus the precision, but turned into a percent. And you can see, and these are both now at log scale, and you can see that there's kind of a trend this way. So there's a lot of stuff. If we have less than 10 examples, we're pretty much always making mistakes. Really rare stuff is super hard. And then you have this sort of cluster in the middle here where like things that you have a good number of examples for, you're usually pretty good at. And then, kind of along that trend. And then you can also create what Eli was talking about, these precision recall curves, and you can do that for your whole data set. You can also break that down by class. And so now you can see, for example, this bat line and the moth line, which I mean, like, why there was even a moth class in a camera trap labeled data set to begin with, like, I have no idea. But these are just really bad. And potentially, if I was looking at this, I'd be like, we probably just shouldn't even try to do that. We probably should just take bat and moth out of this equation entirely. But you can see that generally, what you're seeing is a lot of curves that are really clustered into that top corner. And that top corner is really, that top corner is really like the sweet spot. That means that you're both very precise and not missing anything. And so that's where you want these things to be. Now remember, this is our training data. So like we should be able to completely memorize this, and the fact that we couldn't means that there's actually some stuff that's quite hard. This is training performance, and we're still not seeing things perfect. So, you know, again, just a reminder, like there's tons of different ways that you can poke this performance of the same model. And all of them are giving you different ways to interpret what's going on. And it's really useful. Yeah.
Is this basically running the training data as testing data and just seeing how it results?
Yeah, if you just run the training data through that prediction script, you get those predictions for everything, and then you're now breaking them down into what category are they actually, what category do you predict them as, what confidence levels, breaking things down into like maybe, oh, we'll go into this more, but you can break them down per location. There's different ways to break down performance. Okay, and then this is interesting too. So we can look at what are the most confusing images. So here, what I call most confusing, I think it's quite interesting just as a general concept. It's the stuff that you are most highly confidently wrong at. It's things where your model is maximally confident and also wrong. So I think it makes sense because we're not very confident and wrong. But I think one of the really interesting things we can look at is when does our model wrong and really, really sure of itself? Those things are really confusing. I mean, you can see here is that the most confusing training images, a lot of these it's quite hard to see, but the animals are in there, but they tend to be far away from the camera and it tends to be dark. So things where it's dark and the animal itself is very small, those are just really difficult. This is one of the reasons that we started moving towards more of a detection model, because we knew that we were really struggling when things were far away and when the number of pixels for that thing was small. Okay, so you can do the exact same thing for validation. Here's the sort of breakdown of all these plots for the validation set. This is again randomly held out, same training locations, but just data that wasn't seen during training. So you wouldn't expect to memorize this, but it's still in distribution. So here, you know, you can see the number of annotations per class versus the training data, some similarities, not identical. You can look at the sort of precision and recall, confusion matrices. You can see that there are actually, again, similarities here, which makes sense because it's in distribution. We'd expect it to perform sort of the same here. And, you know, more of these curves are not all the way in the corner, but we're still seeing precision recall curves that look, let's say, pretty nice. Pretty close up towards that corner. So you can make all of this stuff for validation data too. One of the things that we thought was quite interesting is, so if you're now looking at the most confident, let's say Bobcat images on your data set, these are things that you're, that we actually got correct. So this is like things where it is a Bobcat, our model predicted a Bobcat and it was correct and the confidence was very high. You can see in a lot of these, like the Bobcat is reasonably close to the screen. You're sort of getting like a pretty good view of the species, kind of makes sense. You're looking at the most confusing Bobcat images. Again, you'll have weird stuff where there's like maybe a really strong flash or stuff is really dark or things really far away. Those things are confusing. This one was really elucidating for us. So here's our most confident raccoon images on the validation set. These are all the images that we were really confident were raccoons and we were correct. Here's all the most confusing raccoon images. What do you guys see? What was the big difference there? Daytime. So our model had learned it prior, since raccoons are often nocturnal. Our model had learned that raccoons happen at night. And we wouldn't have caught this sort of trend if we weren't visualizing the examples of the data. Okay, so then let's move to testing out of distribution. So now these are sort of, yeah.
It's sort of related, not related, but I noticed you have overlapping classes in some cases in there. Like you'll have small mammal, but also raccoon. Like how do you deal with something like that?
So remember I said this was the first model we ever tried on this. And then after this, we actually made a bunch of decisions about stuff like that. I think it's really important to not have ambiguity in your labels. And I'll talk about that in a second on the out of distribution data. But basically, what you do not want to have is bird and also sandhill crane in your model, because then you're making your model, like some of the time, like it's technically correct if it predicts bird, but you're penalizing it. So what we ended up doing for the actual paper we run on this data is we just basically said, we'll go to the lowest granularity of the class set down each sort of taxonomic branch. So if we had one entire project where they only ever just said bird, then we mapped everything in the other projects that had more fine-grained labels up to bird as a starting point, just to remove that ambiguity. But this is like a big issue when you're talking about what Ben was talking about, which is bringing together data from a bunch of different organizations and trying to figure out how to train models across them. Because everyone has different ideas about what they think is important. And if you're someone who's researching individual bobcats, you are not going to invest the time and effort to label in like bird species. But if you're someone who's interested in bird species, then like you really want that. And so there's this sort of interesting trade-off that we run into where it's like people spend the effort on their sort of relevant research things. It means there's a lot of like bycatch in ecological data. And this is kind of like an open research question of mine, which is like, how do we get access to all the information that's in everyone's data that they didn't label because they didn't care about it? Yeah.
Is it ever common to like do some hierarchical classification, like conditional on it being a bird, try to do it more fine grained or?
Yeah. So, and Grant Van Horn has done actually a bunch of different explorations of this on iNaturalist data. My understanding is that what they found is you could train this whole hierarchical classification thing where you have like different levels of the taxonomy, and you can turn on or off the loss at different levels of the taxonomy based on whether or not you have that level of the taxonomy in your label. That's all very complicated, and it tends to be pretty good, but you could also just kind of like, I think in practice, they found that it's, you just take the stuff that's labeled to species, because for them, they have billions and billions of training examples. So they just take the best data, they train on that. And then what they do, which we do also with Wildlife Insights, the camera traps, is we do like sort of label roll up. So we use taxonomic information. And so say we predict, and there's not a single prediction at the species level that's sort of very confident. We'll like sum taxonomically and now say, okay, well, what's our confidence aggregated to the genus level? And if we then pass some confidence threshold, it's like, okay, we're not super certain about the species, but we're very certain that it's in this genus, then we'll return that to the user instead of making predictions that we're not confident about, because we don't want people to use predictions we're not confident about in their ecological research.
Cool.
So there's ways to use that taxonomy during training, but also post-processing. Okay, so out of distribution. So this is now looking at breaking down those test results per location. The first thing that really stands out is those precision recall curves got whack, right? Now, that doesn't mean that this model is not useful at all, but it's also really interesting how variable they are. And you can see here that like maybe for C4, remember that was the one that sort of performed best overall out of those test sites. There are quite a few classes where we could reasonably trust performance of the model on that location. And then there are things that maybe we'd want to, if the model is saying it's this thing, maybe you just would want to have a human check it still. And so you can look at this type of thing for your, for a given test set, for a given place you want to use a model. And you use that to make decisions about when you should and shouldn't trust a model and what you should basically ask humans to label versus what you can try to label automatically from the computer vision model. And this gets very nuanced because now you have to think about trade-offs between like risks of mispredictions for your class set, all these different like dimensions of complexity in terms of like how do you decide when you should predict a given class, when you shouldn't, but it is useful. And it's kind of like a different way to think about estimating your uncertainty on a given class. It just gives you a little bit more information about whether you're like missing things of that class or whether you're sort of over predicting them. So again, most confusing images coming from one location, a ton of stuff that is being mistaken. One thing that was quite interesting is we started poking in and we realized that there was a lot of examples here where the actual human label was wrong. Mm-hmm. This was my first introduction to the joys of ecologists think they're perfect, but they're not. So this is a really nice way for you to start probing the accuracy of your labels, is you can look at these most confusing examples. In many cases, the most confusing examples, the ones where my model is the most confident and it's wrong, actually the label's wrong. And that's an interesting way to think about cleaning up your labels. The most confusing images from this Mexico camera, where it was like quite difficult, you can see that the perspective of that camera on the scene is kind of different from the other ones. It's a little bit looking down, it's further away. That's kind of the big takeaway I got from it, was that like there's a significant sort of perspective shift on the animals. And then also, because it's further away, the animals tend to be very small. The most confusing images in this like C4 space, this is where we get into label ambiguity. This one was sort of looking at a trail. There's a ton of examples of humans walking their dogs. And because it's image level classification, we had human and we had dog as labels, but this has both. And so your model might say dog, but the label is human, and now you're penalizing it even though it was right. And this gets into like this multi-label prediction space that Eli has done a bunch of really cool work in. So if you think you might have ambiguous labels of this type, I would talk to Eli about different ways to think about handling ambiguity in your label set or missing labels in your label set. And then if you look at the most confusing images at this site, one thing that stands out to me is there's a lot of examples of these like weird perspectives on an animal where like the animal's very close to the camera and you're getting kind of just like the tip of an ear or something. So again, like this helps you kind of understand what are the things that are hard, what are the things that we're failing at in a very visual and like sort of qualitative way.
Should you include those images in your training data?
Well, these are all test images, but we do have images like this in our training data. And one of the things that we've been looking at a little bit recently is taking more of an information theoretic perspective to looking at the training data and trying to like downsample the amount of sort of training images we're looking at. So don't keep a bunch of repetitive images during training, but also getting rid of stuff that's really confusing. And it does tend to help. But again, these improvements this is like in the realm of computer vision's really good at handling some noise in the labels, especially during training. You really want a super clean evaluation set, which is what we did not have here, obviously, because you need to be able to trust that the numbers you're predicting on your evaluation set, if you do better, it should be better. And if your labels are wrong in your test set, which is what we had here, then you can't trust the numbers very well. But if you have some labels that are wrong in your training data set, there have been studies that show that you can randomly flip the labels for sometimes 10, 25% of your training data and still get similar results. It tends to be pretty robust to mislabeled training data, which is another one of the reasons that things like Ben Weinstein's weakly labeled things tend to work well. Because if you have enough data and a bunch of it is wrong, but a bunch of it is kind of right, it can learn that to sort of bootstrap that kind of right into something that's more right. So another thing we looked at is, okay, well, it seems like we're pretty bad at classification, especially in some scenarios. But then we took this first step at like, well, maybe we're learning a good detector. Maybe we're learning something at the class level. So now just classifying empty versus any of the animal classes that actually can give us detection of animal versus not. So this is something where you can, like I was saying, you can walk your way up the sort of label hierarchy or the label tree and try and figure out, okay, maybe my model's not doing super great at what we wanted, but I can try to understand what part of the process is failing, or is there something that I think I could do well. So here, this confusion matrix, empty, not empty for the validation set is very good, right? We're looking at like 99%. Sort of like in those two corners. If we go to these different test sites, what we see, which is actually quite nice, is that for most of them, and even here, the not empty, like the ones that actually have an animal in them in the true label, we are almost always predicting are not empty. But what we do have on the other side is there are quite a few examples that are empty that we're predicting as not empty in like here, here, and here. So these three sites. Now, when you have something like this, what this means is you're You're just also finding other stuff, so you're gonna need to do a little bit of human filtering on those predictions after the fact. But you could pretty much trust these to run through and find the animals. And then you can go through the animals they find and check them. But the fact that this bottom left corner, which is basically would be our false negatives, the things that we miss, is really low in all of these cases, means that this is still something that could be very useful, even if it's not doing everything you want. And this is just classification. And then this was sort of the inspiration that took us to actually start looking at detection, trying to understand how we could build something that would be really generalizable and find animals well. Okay, so more ideas for how to poke stuff. One thing we also looked at with the Caltech camera traps data, and this was now from the papers. This is like the cleaned up version of the data set, and like, you know, some other things have changed. But we looked at plotting error versus the number of training examples. So that was that plot that I had before that was kind of speckly. Now we took a best fit line through those, and we plotted them for images by frame. Now this is classifying the whole image, but then we also looked at, again, moving towards more detection standpoint. If you pretend you have an oracle and you just look at classifying inside the box, how much better do you do? And so this reduction in error at the cis locations and the trans locations really points to classifying inside the box is a much better paradigm for camera traps than outside. And then the rough, like the blue line, is looking at per frame performance, but these are sequences of images. And so we also looked at just really simple metrics for aggregating. So just taking an average or taking a median over the predictions in a sequence as a post-processing step to incorporate temporal information. And you see, again, consistency, this improvement in performance by just aggregating over time. And for someone like Catherine, where you have these temporal sort of sequences, you can look at predicting for every single frame. And one of the simplest things you can do is then just take averages over windows and look at performance on that to try to get a sense of how much improvement you can get from this sequential information as a post-processing thing as opposed to pre-processing. Another thing that you can do when you have these really imbalanced data sets, and this is now a plot from a recent paper on urban forest monitoring where you have this very imbalanced distribution of species, is you can look at breaking down performance by the amount of training data. So instead of looking at every single class and their performance, you can say, okay, let's look at only the frequent classes, let's look at only the common classes, and let's look at only the rare classes. What we found here is that basically rare class performance was essentially 0. Frequent class performance was like in the mid to high 90s. So we have a model that's reasonably trustworthy on the most common species of trees, and there's a lot of room to improve on the rarest species of trees. And now we can start thinking about, okay, so given the model we have, what can we use it for ecologically now? And what do we need to keep working on the hard stuff for later? This is the way that we looked at visualizing performance versus distribution shift. So here, this is just roughly looking at the sort of distance in distribution space for these different cities. Now looking at a train on one city and test on another city. What does that performance look like? And here, this is the actual accuracy of these models if you do that sort of pairwise training. And you can start to see that there are these blocks that form. There are these sort of strong correlations between similarity in distribution and performance. So just lots of different ideas about, and you can think about for you, like what are the ways to do this? Just ways to poke at your model and try to understand the patterns. Other poking ideas, you can look at performance day versus night. If you're doing remote sensing, one thing that's quite cool is there's pretty good off-the-shelf cloud detection models. And so you can look at percent of cloud cover versus performance using something like that. So like trying to explore how much cloud cover is affecting your ability to predict the class that you care about or the things that you care about. You can try looking at visualizing false positives per sensor. This might relate to both bioacoustics and to like things like camera traps, static sensors, or potentially there might be repeated sort of background information. So you just visualize things that are being detected in the same place over and over again over time. Also might relate to your stuff with the camera traps and weather. If you're always getting detections in the same place, then you could actually just have a step in your actual system that tries to look at those and lets a human filter them out really easily across all of the data. We do this with camera traps where we like, hey, this is an out of distribution camera trap. we're getting a lot of predictions in the exact same place. Could you just check it and make sure it's not a rock? And then if it is, if they're like, human looks at all of them, like, yep, that's a rock. Then you just remove all of those predictions at test time or sort of at deployment time. And it really speeds up the amount of human, like, correction you need to do for the machine learning like this. Okay, so what is a model? This is just like a couple things that can be useful when you're trying to understand in this black box system, why is it wrong? Because sometimes it can be really confusing. So one thing that's kind of nice about more structured prediction is that this comes a little bit for free. So you have more complex training labels if you're training something like detection or segmentation, right? They're much harder to collect. And the models can be more finicky to train, but it does give you slightly more interpretable results. So here, if this is your classification model, it just says zebra. Especially if you're going through data quickly, you'd be confused by this. But if you get something like this, then the human who's actually checking the results gets their eyes drawn towards like, what is it saying is a zebra? And if you look very closely in here, you're like, it's actually right. There are zebras there. And so these structured model predictions can help you interpret what's going on.
Those zebras are elephants.
Huh?
Are those zebras or
Elephants.
They're grubby zebra. You can kind of see the stripes right here.
Yeah, actually see it better.
Here. So again, here, say you got this image and it said skunk. You're like, what the heck? It's obviously not a skunk. It's structured prediction, and it's telling you it's a skunk. You're like, oh, this was a real example. Like, okay, I mean, that's kind of annoying, but like, I get it. But this is also something where then that maybe false positive filtration might catch this repeated detection. And then another cool thing, which is like in this area of interpretability research for classification and for some more structured things as well, you can look at is stuff like saliency maps. This is something, I pulled this directly from an off-the-shelf tool called FlashTorch that does a lot of different visualization of model results, so you can move around in there and see what might be relevant to you. They have a collab demo of these saliency maps. But here what you're looking at is essentially, given an input image, what are the things in your model that are most contributing to its decision that this is the class that it thinks it is? So you can do these per class. But here, you can actually see that for this owl, sort of strongest features that is making it make a prediction of owl are around the eyes. Whereas here with this peacock, you can see it's really focusing on like those peacock eyes, like these things. And so this is actually the way we figured out in the end that logo thing. And we're like, why the heck is it predicting this animal? It's like nowhere near there. It's nowhere in the training data. So another way to try to figure out what your model might be learning that's not useful. Another thing here that's a big red flag is if you build these saliency maps and it's looking all over the image and not actually sort of focusing on the object, that's a good sign that maybe it's not really learned what the object is. And then, like,
Are these maps from like a specific layer inside the model, or?
So you can, there are many different ways to try to poke this, and there's a bunch of different methods that people use. Sometimes they look at activations in a specific layer. Sometimes they do aggregation over layers. I picked that one because there was a really nice, easy to use tool where you can directly drop things in, and they had it all implemented. I don't think you get very, very significantly different results using the different methods. With the layer activations, then you have to pick which layer you want to use, which can be kind of, it just feels like a little hand wavy. Like if there's like this famous thing where like, if you're using an inception model, people always look at FC7. You're like, okay, like there's just like this random layer that people just like to look at in terms of like the activations in that layer for inception models. And it's just, it became this sort of like weird meme when everyone was using inception models. It's like, oh, FC7 again. But it feels a little cherry picky. That's okay though. Like it's okay to cherry pick stuff for just like qualitative visualization. You just want to like realize that you're doing it. Uh-huh.
I was just gonna ask, with the saliency maps, would you use that on your training to test your training data or your validation data? Or
Well,
maybe
you could
both?
use it on anything, right? What you could say is like for your training data, you'd sort of hope maybe that it would be quite good, but it's also seen those examples before, so it's possible that it is maybe looking at memorizing some stuff that's not the actual object in the training data. If you look at this on validation data and it's looking at the sky, for example, you're like, that's probably not a good sign. But any of this stuff, like that's the thing I wanted to point out at the beginning, is you can use this on any set of data. You can look at, let's just look at only the training data examples from like my rarest class and try and figure out like, okay, is it learning anything about this class? That kind of thing. Yeah.
What if you're doing it on your validation and it's shown that it's just sky? What would you do? Like just go back to your training data and
Well, what we ended up doing was switching from a full image classification to a detection task, because we were like, it's not learning to disambiguate foreground and background for this specific task. But I think it's just another way to think about like, if you are like, oh, it's not learning this thing, and you can kind of start to understand for yourself what that is, then you can make choices about how to address it. Whether that's like changing the task that you're doing, collecting more training data and labeling it, maybe if it's really imbalanced, you think that's a big issue, maybe trying some class balanced like loss functions during training. But you can use this to inform the choices you make about what to try next. And then the last point is that, again, we were looking at all those grids of image predictions. You don't actually need labels to explore model results. So even just something as simple as take your model, run it on data, and then just make a grid of everything it's predicting as a cow over 90% confidence. Everything it's predicting that's a cow between 80 and 90% confidence, and just sort of drop through your confidence values. That'll give you some intuition around like what the model is doing, the calibration of it in this very qualitative way. This is exactly what we do with new mega detector users. We basically generate this HTML page. We take 10,000 examples of images from their data randomly sampled. We run our model over all of it, and then we just make these links that take them to these just blank pages where they can scroll through images and look at the boxes on the images and say like, okay, these are all the really high confidence detections. These are our really low confidence detections. Try and figure out for themselves, like what's maybe the operating point, like maybe what confidence threshold makes sense for their project. But also helps them really quickly decide, like Jen said before, is this just crap for me? Before they invest in really trying to like use the model themselves, building up a whole data infrastructure, investing in this thing, and then finding out it doesn't work. Like, let's make it really easy for them to say, not yet, like maybe later, because we don't want to waste anybody's time. Another nice thing there is that you can, once you have these checkpoints, you can build a collab demo, like just a collab where you can load in those model weights and let people just upload any of their own images and get results for them in a way that doesn't mean they have to install any Python. They don't have to like do anything complicated. And it's just this really nice way for other people, or even for yourself, to just try very, very simply, try your model on some new stuff. And again, a lot of this is about building intuition for your own model. And some of it is quantitative, but a lot of it is qualitative. But what we found is that it's qualitative, that intuition building helps you find the stuff that's a problem. It helps you find these red flags. It helps you figure out, what do I need to do to try to make this better? Cool. That's the end of that. Happy to take questions. And beyond that, depending on my time, I might try to create a predictions function for Benny's example code base, just as an example. But it depends on how many other fires I have to put out today. So, cool. Any other questions before we go to lunch? Awesome. I think everyone's hungry. So let's go to lunch, and feel free to feedback.